Welcome back. Hope you're doing well. Last time we were talking about monotonic and exponential functions. We talked about these two things because they end up being important and playing a role in terms of their inverse functions, right? Exponential has inverse functions, and we know that because the exponential is a type of monotonic function, which we actually know a good bit more about its inverse function. We know that it is continuous and that it is itself strictly monotonic if the base function itself is continuous and strictly monotonic. So we discussed some of these things there. Now, we are wanting to be very rigorous as we go through this. And you might have noticed that when we went through the exponential function, you might have been like, yes, yes, I know a lot about this stuff when it comes to the exponential function. But the reason that we're trying to build it up in this way is that we want to be able to use these properties to be able to know more and prove more about these sorts of functions. The more things that we know about these functions as we keep going, the more that we can start proving things with them, things that start feeling a little bit less intuitive, perhaps, than the fact that 2 to the x plus 2 to the times 2 to the y is 2 to the x plus y, right? And things like this. So we want to make sure that we have these things solid, down pat, so that we can move forward and start really proving things with them. And we're going to see that a little bit here in today's presentation, because in talking about the derivative, we are going to need to be able to use some of these theorems and things that we have been building up for the derivatives of these functions. Once we go through and do the definition for this derivative, we're also going to go ahead and jump straight to the differentiability theorems that we're used to. Sum, difference, product, power, all of these sorts of rules that take place whenever we're taking derivatives here. But we're going to go ahead and start by defining the derivative. Sometimes this is not the way that it is defined in a particular textbook, although it is an equivalent condition. Oftentimes when I look in calculus textbooks, this is the definition that I usually see for the derivative. Is the limit as h goes to 0 of f of some fixed point x naught plus h minus f of x naught divided by h. And the way that you may have been taught this is that this is a limit of slopes, or the slope of a tangent line of a particular function. And the question is that when is it that something like this exists? And we're going to only be able to deal with specific functions with this definition whenever we say that they are differentiable. That is, whenever this limit exists and is finite. Okay, so this is going to be whenever we have a function f defined on some interval. Note now that we're moving away from the fact that we're looking at just a general domain and only looking at accumulation points. We're going to start by dealing with things that are differentiable on an interval here. Notice, by the way, also that you could potentially imagine something that has an infinite slope for its tangent line, but we're asking for a function to be differentiable only when the derivative exists and is finite. So for example, something like f of x equals x to the 1/3 would not be differentiable on the interval from -1 to 1, even though this function does indeed look like it is nice and continuous and at least has some tangent line as we go throughout there. Here at the point x equals 0, that tangent line that we draw is going to be vertical, and hence is going to have an infinite derivative whenever we try to go through and define that. So we're going to ask for something to be differentiable on this function, on this line, which means we're going to ask for it to be finite. So this example is not differentiable on the interval from -1 to 1. Of course, if we had done something from 0 to 1, not including 0, that would have been extremely fine as something being differentiable. We're going to denote this limit as f prime of x naught and call it the derivative, and that's what we're going to do. We can also define one-sided limits here for right-hand and left-hand derivatives if we just take a look at right-handed and left-handed limits, respectively. So one or both might not exist, but you might be able to determine whether or not a derivative exists by looking at its right and left-handed limits and seeing if these exist or not, or if they end up being equal. So if we have I being the interval going from a to b, the closed interval now, we have to ask again, okay, what do we mean if this function is only defined to the right of a? Well, then when we talk about the derivative f prime, then we're going to be talking about it as f prime plus. We're going to talk about it as the right-hand derivative for that function. But for most of the time, we're not even going to be looking at derivatives in terms of the closed intervals. A lot of our functions that a lot of our theorems that we're going to be using are going to ask for our functions to be differentiable on an open interval. So we aren't going to be seeing a lot of this very much, but we'll kind of give this an essential understanding whenever we end up potentially seeing a closed interval in our homework, for example. Now, the derivative has a lot of different notations, a lot of different ways to be written. So we can write this as f Sometimes it's written here as a dot above the f. I see this actually a good bit in differential equations. df over dx is one way to write it. D sub x, where D is the differential operator that we might be a little bit used to from before. And then the subscript of that differential operator is going to tell us what variable we are taking the derivative with respect to. Another way that it can be written is f to the, in parentheses, how many times we're taking this derivative. F to the 1 in parentheses is going to be taking the derivative just once. But you could see f to the 2 in parentheses to mean the second derivative of a function. So value of the derivative function at a point is defined in this way. Now that we've defined the derivative as its own function, we can start analyzing it as if it has its own function properties. Is it increasing? Is it decreasing? And things like this. So these are the sorts of things when we put everything together, we can define a new function out of f, right? So remember that we kind of have already seen this in terms of our world of abstract, of functional vector spaces. We're taking the differential operator of f going to f prime. This f prime is its own function whenever we're looking at smooth functions, for example, on a specific interval. But d is not the function that is going to be called derivative here. We're going to say the derivative of f, and we're going to be calling f prime this function. So we're not quite looking at the differential operator right now. We're only looking at f prime, the function that comes out of the differential operator. Examples of differentiable functions. We can see some of these by using the examples. For example, 1 or any constant function has a derivative of 0. The derivative of x is equal to 1, and you can go through and try and do some of these things if you would like using the definition. For example, the fact that x prime is equal to 1, you can look and say, okay, well, how am I going to use this definition here? I'm going to say that this is the limit as x approaches x naught for any value x naught that I'm looking at of f of x minus x f of x naught divided by x minus x naught. Well, I'm going to plug in what I know the function to be. I know the function is x, so f of x equals x, and f of x naught equals x naught. So this is x minus x naught. Once I take that limit, this is what I end up getting here. And this is going to give me the limit as x approaches x naught of 1, which I know to be 1. So that can be one way I can go through and do that. I can also do similar things, although they end up taking a little bit more time and sometimes involve some algebraic manipulation of taking derivatives of things like the square root of x that get 1 over 2 square root of x. Using some of those formulas that we were talking about before, remember that we said, for example, that sine of x over x, the limit of this as x goes to 0 is 1. Using formulas like this, we can also use this formula to try and use the fact that sine of x's derivative is cosine of x. Might be good to look at those sum and difference formulas for trigonometric functions as well when you're trying to employ the derivative definition here. And I'll let you try and do that on your own time. It's something I highly recommend because I think it's a good exercise to see why the derivative of sine is cosine. We can also do some expansion to show the derivative of x squared is equal to 2x, as well as the derivative of 1 over x is negative 1 over x squared on its domain, of course. So we get to see here how some of these things work. I've already shown the one for the identity function. We have a similar thing here for the constant function, how to go through and actually find these derivatives here. So this is using that definition and taking limits wherever we need to. And notice that here, it's okay for us to use the limit as h goes to 0, or we could have gone up to this example and then the limit as x goes to x naught. It just depends on how you would like to go through and plug that in, because at the end of the day, they're very much the same thing. Then we have the formula here for f of x equals square root of x. I noted here that we would have to multiply times a conjugate in order to make this one work. Or better to say here, it looks like I can actually write x minus x naught as a difference, as a product of using a difference of squares formula as a product of two conjugates. So if I go through and cancel things out, then I should be able to get what I'm needing right here. Notice that here, for example, we have to start separating out what kind of domain we're looking at for square root of x. In the case that x naught is greater than 0, for example, this is what we end up getting is 1 over 2 square root of x naught. But in the case that x naught is equal to 0, we end up getting an infinite derivative. So for example, f would be differentiable on the open interval from 0 to infinity, but it would not be differentiable at 0. And this makes sense because when we think about the derivative of this function, which we got to be 1 over 2 square root of x, it makes sense because this kind of function is not going to be defined at 0. However, we can't just use the fact that whenever x naught is greater than 0, look at this and say, oh, well, if I plugged in 0, this wouldn't exist. Therefore, the derivative does not exist. That's because we assume that x naught was greater than 0 here, we had to make a different case when x naught was equal to 0 instead. And then whenever we did that, that gave us something a little bit different. So we had to actually deal with that case separately and give it its own part of the definition. So keep that in mind. It's not enough to just say, oh, okay, well, I assumed this when x naught was greater than 0. So if I plug in x equals 0, it's just going to be infinite. That's not enough because our condition here was that x naught was greater than 0. Now here's that sine of x formula using these sum and difference formulas. We can write sine of x minus sine of x naught in the following way. Using that this is 2 times sine of x minus x naught over 2 times cosine of x plus x naught over 2. We've used this formula once before. Then what we can do is we can write out what this is, where we can take g of x naught to be this kind of inside function, this little bit of x minus x naught over 2 business, and take a look at what this should be separately, while also multiplying it times cosine of x plus x naught over 2. Now, keep in mind, x and x naught are about to be approaching each other. So this is just about to be cosine of x plus x naught, a cosine of 2x naught, or rather cosine of x naught inside of this factor right here. But we need to be a little bit more specific about what's actually going on here. Well, we know this value is going toward 0. G of x comma x naught is going toward 0. This limit here is going there towards 0. Well, whenever I take the limit of sine of y over y, I know that that's going to be equal to 1. Well, thanks to the fact that a lot of this is looking at continuous functions, I can now assume that the limit of this entire thing then, as the composition of these two functions, is going to be equal to 1. Well, if this is equal to 1, then the only thing that I'm really getting here is that this is the limit as x approaches x naught of cosine of x naught, like we said before. So this gives us what our derivative of this function is going to be. Now, a neat little theorem tells us something that we often take for granted, which is that differentiable functions are automatically continuous. We never had to assume this whenever we were making the definition, but differentiability does imply continuity. Remember that continuity is the thing that says that f of x minus f of x naught grows to be very small whenever I choose a delta window that is of an appropriate width. And so remember that the way that we're going to try and do this is to attempt to show that the limit as x approaches c of f of x is actually equal to f of c. And to do this, we get to use the fact that the derivative exists and is finite. We're going to need finite here in order to be able to move forward with this. So here's the way that we're going to do it. We're going to write f of x in a specific way, where here f is the function that we know is differentiable at a point c. So how are we going to do this? We are going to write f of x in the following way. We're going to start by writing it as f of c plus f of x minus f of c. If we had canceled out the f of c's here, we'd just be left with f of x again. And then we're going to take the second term and we're going to divide it and multiply it times the same thing, which is just x minus c. Now this thing on the second term, the left factor, looks a lot like we can start looking at finding it as a derivative. And since we're taking a limit outside of here, we can take a limit of each of these two terms. Taking a limit of f as x approaches c of f of c is just going to give us f of c because that's a constant with respect to x. The other stuff I can break up in terms of the limits that exist for each of these two numbers. Notice that I can do this because I know both of these limits exist. Both of the individual limits exist because this one on the left is now the derivative f prime of c, which is a finite number, times 0. Limit is x approaches c of x minus c. That limit is going to be 0. I don't have an infinity times 0 business thing going on, thanks to the fact that my derivative is finite. So this just gives me f of c. Well, that's exactly the definition of something being continuous. Similarly, we could look at if you have a right-hand or left-hand derivative at a particular point, because you're only differentiable on a closed interval, and you're looking at just the endpoints here, then you can get that the limits of these functions coming from the right or the left, respectively, end up looking like you want them to as well. Now let's go through and talk about these differentiability theorems. We take a lot of these for granted, and sometimes it's merited because it's just using the definition in a way that kind of makes sense. For example, the sum rule kind of makes sense to us because if you take the derivative of the sum, that's the sum of the derivatives. And you can try and see that here as we break apart this limit formula. If we try and take the derivative of f plus g using the definition, then you can just break apart the limit in terms of the stuff that has f in it, the stuff that has g in it, keeping the denominator the same throughout, thanks to the fact of that's just how fractions work. So that gives us these as our derivative formulas, and that gives us f prime plus g prime. We could also use the formula in a similar way to multiply times a scalar multiple, r times f. That would also be differentiable. And the constant is just going to be able to come out, essentially because the constant can come out of this numerator, and then the constant can come outside of this limit. So a lot of neat ways to see this here, especially now much more clearly, thanks to the fact that we've seen limits of functions a little bit from the previous few discussions. Now, product rule is a little bit of fun. Product rule has an interesting proof because it ends up asking us to add and subtract by the same thing. And this is a common trick that's used in analysis and in other parts of math as well. It's trying to figure out, okay, how am I supposed to break apart something that looks like this? If I went through and plugged in what this is supposed to look like in terms of the derivative formula, then I'd be left with something like this. I'd have f times g of x minus f times g of c over x minus c. Now, this one's a little bit tricky, right? I don't quite know how to be able to write something like this with tools that are given to me, but I need to try and find something in common so that I can start factoring out of a formula that goes f of x g of x minus f of c g of c. But right now, there's nothing in common between those two terms. I can't factor out an f of x, an f of c, a g of x, g of c, unless I start adding and subtracting by the same thing. The thing that we're going to add and subtract here is going to be g of x and f of c. If we subtract that over here and add that over here, of course, everything here is getting divided by x minus c, and everything here is getting divided by x minus c. Then what ends up happening is I'm adding and subtracting by the same thing, so I haven't actually changed my expression. But what happens is now I can find some common ground between the following. I have this f of x g of x right here, and I have an f of c g of x in the numerator that I've subtracted by. So I can group those two things together and factor out by g of c, or rather g of x. Now, what I have left is f of x minus f of c over x minus c, and that should look a lot like the derivative. Similarly, now grouping together these other two parts, let's do it in a different color, f of c g of c and f of c g of x, I can factor out an f of c, and what I'm left with is something that looks like the derivative of g of x, this part right here at the point c. So now we're going to go through, take a limit of everything here, getting a limit of this times a limit of this, limit of this times a limit of this. And the fact is that we're going to use the fact that g, being differentiable, is continuous to conclude that the limit as x approaches c of g of x is, you guessed it, g of c, so that we can use that as part of our formula. So this is multiplied times the derivative of f at the point c, because that's just the definition of it here. And then here you have this first factor, which is just a constant with respect to x, so it gets carried over. And then this part, which is the derivative formula for g. That's where our product rule comes from. It comes from this interesting adding and subtracting rule. Now, the reciprocal rule is something that we can use as kind of like a midway point between using the product rule and going toward the quotient rule. The reciprocal rule says that if you have a function that is differentiable, then 1 over f is also differentiable on its domain. All right, so in particular, we ask for f of c to be not 0 at any point that we're looking at. So what we need to do is just kind of check out, see what happens. How can I use this reciprocal rule to go through and make this work? Well, if f of c is not equal to 0, then there's going to exist some neighborhood where the function is also non-zero. And that's thanks to the fact that this is a continuous function. So we start by using the fact that f is continuous to show that this is a little neighborhood here where your function is also non-zero. That way we can still be talking about, okay, we can still put function values here in the denominators of specific fractions and not get in any trouble. So here's how we're going to do it. We're going to first plug everything into the derivative formula, write everything out in terms of their fraction form, and then start combining things together by getting common denominators. That's exactly what we have right here. So when I take a look and try and just combine some things together here, I notice over here on the right-hand side something that looks like what I'm looking for. Namely, this looks a lot like f squared of c. It's f of x times f of c, but when I take that limit, I should expect to get f of c quantity squared. What I have here on this other side looks a lot like the derivative of f. once I've gone through and gathered that. So that was my goal essentially in trying to algebraically manipulate this, was to get this into this sort of form. Indeed, when I go through and break apart that limit, since they have a product of two things, that limit of the product is the product of the limits, I go through and find that this is the derivative that I get. Now, I said that that's a midway point to the quotient rule because we can use that to help us out. First, the difference rule, we know that this one works nicely because we know negative g has a nice derivative thanks to the homogeneous rule, and then you can just use the sum rule to help out at the end there. Now, the quotient rule has this strange formula, but the thing is that this strange formula works and is derivable from all of the other things that we've done so far. Because really, what is f over g? F over g is just f times 1 over g. And we know that each of these things is differentiable. Each factor is differentiable on its own. F is differentiable, and 1 over g is differentiable wherever g of c is not equal to 0. Of course, wherever in the domain of f over g. So because of that, we know that both individual functions is differentiable at a specific point, and hence by the product rule, we can find the derivative of this function. And if we just go through and walk through that, then that gives us what we're looking for. This is an exercise that I make sure that my undergrad students go through a good bit, because I want them to see that the thing that they're trying to do, or that they've just learned is true this whole time, this low d high minus high d low over low squared type of thing, is something that's always been there, right? It's something that works very nicely with the other rules and stuff that we've been building up. So this is that reciprocal rule. Now we get to the power rule. The power rule is one of the things that we're usually given very early on when we're trying to learn some of these derivative shortcuts, if you will, for these functions. But the power rule is one of the hardest to kind of get your head around when it comes to the proof of it. And it's due to the same reason as to why 2 to the pi is hard to get your head around. It's the fact that trying to just say, okay, the derivative of this is going to be bringing down the pi and things like this doesn't work very nicely in terms of trying to figure out, okay, I have something like x squared minus c squared. I know how to factor that, and I can get that to work nicely if I'm dividing that by x minus c, like I should be in this formula. But something like x to the pi minus c to the pi, I don't quite know how to factor that very nicely. It's just not as nice. But we can start somewhere. We can start with the natural numbers. Here, we're going to start with the derivative of x to the n and show that that follows the power rule that we all know and love very well. The one that where you bring down the power and subtract 1 from the power that exists. Nx times n minus 1 is the derivative of x to the n. This is a proof by induction that utilizes the product rule. If you have the derivative of x to the n plus 1, that's just the derivative of x to the n times x. And you can use the product rule to figure out what that ends up being. It becomes a very nice sort of formula here that ends up stacking on itself very nicely. We note also that the way that I was describing it is also by using this formula for x to the n minus c to the n divided by x minus c. Now, we can also do this for negative integers, x to the negative n. Note, we're not including 0 here. X to the 0 we know is 1, and we know the derivative of 1 is 0. So dealing with negative integers is as the power of these functions. We can also figure out what this is because, well, what is x to the negative n? It is 1 over x to the n. That is a reciprocal of a function, so we can use the reciprocal rule to figure that out. And it gives us the nice formula that we have here. But that's all we're kind of able to do right now. We've gone through and done for some things and shown that this works for things like x to the 1/2 in some previous examples. But we're going to talk a little bit more about some other stuff before we get back to looking at these functions and how these things can be derived. And to do that, we're going to be looking at something. Let me make sure I'm saying this right. I'll come back to that actually in a little bit, because we'll talk a little bit about this while we are discussing something called the inverse derivative rule, right? Or the inverse function theorem. And so we'll discuss this, that sort of stuff a little bit later on. For now, let's move on to another rule that we love getting to see, which is the chain rule. Another one that kind of like, you can get the idea of it, handle of it when you're in Calculus 1, but the question is why does something like this work? Why is it that when you compose two functions, it's the derivative of the outside times the derivative of the inside, right? Where is that sort of thing coming from? The main idea, the main trick behind it, and there's a couple of hoops to kind of jump through here. The main trick is that you're going to take your formula that you would normally use for the derivative of g of f, And you're going to multiply and divide by the same thing. And that thing is going to be f of x minus f of c. And that's exactly what we have here. Now I can take a look and ask about the limits of each of these two factors. The one on the right, definitely, this looks like when I take a limit as x goes to c, that this is going to be the derivative of f. This one right here is interesting because these, remember, are kind of like the x values for g. These are kind of like the y values for g. In that case, this looks a lot like the derivative of g with the values of f being the domain values inside of there. And intuitively, at least, it makes sense that that is going to become this factor right here. There's a lot of things to be careful about here, one of which is that, well, one, a function f could be 0, in which case f of x minus f of c is going to definitely be 0. In fact, we see now that it could be a little bit more dangerous. F of x minus f of c could be 0 even with just f is constant or close to constant on enough points. So that's something that we have to just be careful of. So if that ever ends up happening, then what we end up doing is we say, okay, we take a look at this formula one more time. If your function f is 0, if is equal to f of c in enough spots around the point x equals c, what ends up happening is that you can say, okay, the function is differentiable here, so I can take limits of f of x minus f of c over x minus c and show that that derivative is actually 0. So if you have that, well, then the formula still works because you're multiplying something times 0, so this ends up being okay. It still just kind of follows in suit. So this gives us the formula that we're looking for. Now we can use this to help us figure out things like derivatives of cosine. We've already found the derivative of sine, but we know that cosine can be written as a composition of functions, x plus pi over 2, and sine, because of this sort of formula here, to get us the formula for this being derivative of cosine being negative sine. We're just kind of following our nose a little bit here to try and use the chain rule in this way. If we do that, then we get that g prime of x is equal to just 1. And so we have h prime of sine of x, which is cosine, of g of x. We get to plug in what this is equal to. So this is x plus pi over 2 in there for cosine. Well, if you shift cosine over by pi over 2, you're going to be switching over from sine and cosine depending on which direction you're moving in. Here we're moving to the left, so this is going to give us negative sine for that function. Then if you have the f of x equals tangent of x, you get to use the tangent rule, or the quotient rule to give you the formula that you're looking for in this one. So we can now use a lot of these formulas to find any of the derivatives of trigonometric formulas that we have from before. Now let's get to the inverse function theorem. We talked about inverse functions last time, and we needed to have a little bit of a rigorous approach for it, a rigorous handle on it, so that when we moved into this section and talking about derivatives for inverses, we have a lot more ability to prove things in this world. First, let's start with an invertible continuous function. Invertible just means it's bijective. It's continuous, right? So that's going to be useful. If f is differentiable at a point x0 and f prime is not 0, at that point, the inverse function is also differentiable, and we can find that derivative using this formula. Note this formula is sometimes not the one that is given to you in your calculus textbook. Notice here that we are saying f inverse of the y value is 1 over f inverse derivative of f inverse at the y value is 1 over f prime at the corresponding x value. So sometimes the way that this is written instead is that this is 1 over f prime of f inverse of y naught. This being well defined because you have an invertible and hence bijective function. So you have this formula here, 1 over f prime of f inverse of y naught, to give you that differentiable function. Of course, here we want to make sure f prime of x naught is not equal to 0, so then we're not looking at something like a vertical tangent line here. And this is something that, like, having a picture for really helped me understand where this sort of formula came from, right? You're looking at something like if I had a inverse of two functions, right? So maybe I was flipping along the line, y equals x. And you start taking a look at what these slopes end up looking like. This slope right here versus the corresponding value down here once it's down here and flipped. Well, if I want to find the slope of a tangent line in the original function, then I know how to find that formula. It's the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. Now here, I'm doing the same formula, but notice here that my x and y values are flipped. So this is the limit as x approaches x naught of x minus x naught over f of x minus f of x naught, because I flipped the roles of x and y values. Well, if I compare these two formulas, one is clearly a reciprocal of the other. So it makes sense that when you take the derivative of the inverse, you're getting the reciprocal of the derivative of the original function. Of course, this is just an intuitive understanding of the proof, but indeed it is a lot of what the proof kind of relies on. The end of the day is sometimes you have the same issue as what you had in the chain rule. When you ever had the chain rule, sometimes this value here is 0 in a lot of places, and you have to ask the question, okay, what's happening there? It turns out that in the same sort of way that it did with the chain rule, at that point, your derivative would actually be equal to 0 at that point. So we wouldn't be discussing those sorts of things anyway. Another way to do that is to just use the chain rule itself, because we know that the composition of f inverse with f is the identity function. So this thing in particular is going to be equal to 1. Well, if I go through and solve for what this is in terms of f inverse of y naught, prime of y naught, then that gives me the formula that I'm looking for. So these two things kind of very much connect with each other. All right. So here is that little bit of a proof that I was mentioning from before. You can see that little heuristic that I had taking place right here. And the only issue is that at some points, you might start seeing, okay, well, what happens if things are going to be 0 in a lot of places? The only issue really ends up being that particular one, and then everything else works out very nicely. You get this sort of formula here at the end. All right. So this gives us our formula there. That gives us derivatives for things like arc cosine, because now we can use this inverse function theorem to help us out here. So we get to find the derivative of arc cosine here, g prime of fx, where g here is going to be the function just cosine of y, its inverse function. And remember that we can form a triangle to try and figure out what the sine of arc cosine of x is going to be. And that gives us this formula right here. Now, exponential and logarithmic functions are also useful here. One of the big exponential functions uses Euler's number, which is something that we haven't even had the chance to discuss a lot yet. We've kind of touched on it here and there, but it ends up being one of the more useful ones because of the fact of knowing how its derivative ends up working. Well, first, let's talk about a theorem here about how we define E. Let's define E to be the sequence x sub n equals 1 plus 1 over n, all to the nth power. Well, this is an increasing function, and you can tell that a few different ways, one of which is you could potentially try and you can notice that this is a differentiable function whenever you look at it in terms of the real line, and you can look at its derivative, see when that derivative is positive. That could be a neat way to do that. And notably, it also doesn't have any breaks in its domain, so that's going to be fine there. And then you can see that it is going to be a bounded function. One way to kind of take a look at this is to say, okay, well, what does this look like if I try starting to expand it out? And you can try and do some series tests to help out once it kind of expands out a little bit. So this thing is going to be convergent. The limit of this number is E. Now, this part I was confused about a little bit when I saw this when I was collecting my notes and things like this for this, but then I realized that this is a mnemonic for understanding the numbers here for pi. I thought that was pretty fun. I'm 2 letters forming 7 letters, a mnemonic to remember a constant in calculus. Now, this actually is not repeating the 1828. The next number is like 4, 5, 9, or something like this, right? So it's not actually repeating at this point, but it might be a neat little trick if you ever want to remember what this number is. A corollary of this is that you could also write, instead of 1 over n here, you could write x. If you had written 1 over n there, then n becomes 1 over that x. So then that is just the limit now as x is going to 0 of this function, since you're kind of substituting out x for 1 over n. So this gives us a way to find E here as well. So now we have this notion of the exponential function where you could start thinking about plugging in E. We're going to define the inverse of the exponential e to the x function as log base e of y, but we're also going to be calling it log of y, depending on where you went or what kind of exposure you've had to this kind of mathematics past an undergraduate level. You might have already seen this notation, but you might have been more used to its sister notation, ln of y. And the reason is that not oftentimes when we begin introducing logarithms, it makes more intuitive sense to talk about log base 10. For example, log base 10 of 100 is 2 because there's 2 zeros there. It's a great way to help understand logarithms. However, the logarithm that is by far the most useful in any context is the natural logarithm. So oftentimes that's the only logarithm that mathematicians need to worry about. So we just call it the logarithm function. It's just log of y. So oftentimes here and throughout, you will see that log of y is actually the natural log. And if we ever want to talk about log base 10, then we're actually going to write it as such, log base 10 of y. Well, what happens when I go through and try and take some derivatives here for these functions? Well, we know 1 plus h to the 1 over h approaches e thanks to this corollary. Well, if I go through and take, let's see, some logarithms of everything here, then I know that I can do some of those neat tricks that I know logarithms have. I can bring 1 over h down and have it be multiplied out right here, h inverse. Well, this is going to be also log of 1 plus h to the 1 over h, which is approaching log base e, since the logarithm is a continuous function, as we know from before, which is equal to 1 as h approaches 0. In other words, we can now use this formula, by the way. We've been kind of hiding it here a little bit, but this is actually a formula to help us find the derivative of the logarithm function. So the derivative of log of y, at least at y equals 1, which is what this formula would give us here, is equal to 1. And that's going to imply that the derivative of e to the x at x equals 0 is equal to 1. It turns out that when you have those two formulas, you have pretty much the entire derivatives of e to the x and log. Because indeed, after that point, you can use these formulas. You can just factor out an e to the x out of each of those terms. What you're left with is e to the h minus 1 over h. Well, we know that this is the exact formula for the derivative of e to the x at x equals 0, so we know that this is going to go toward 1. In that case, you're just left with e to the x as its derivative. In general, for a to the x, what we end up doing is using the fact that e to the x has such a nice derivative, we write a to the x as e to the something. So we write this as e to the natural log of a to the x, bring down the x, get e to the x log of a, and then use a chain rule on it. So this is just a to the x times log of a when I go through and simplify that. Similarly, for the derivative of log of x, we get that this is going to be 1 over x using the inverse function theorem. Now that we've done all of this, and it seems like we've taken quite a trip to get here, we can talk about the power rule in a more general case. In general, now we can look at this in terms of any real number as our power. And the trick that we're going to do here is we're going to use that exponential function. We kind of already did this whenever we worked at the derivative of a to the x up here. But now that we have x to the alpha, right, now x is still a variable here, but it's out in the base instead of the exponent. We can still write x to the alpha as e to the log of x to the alpha. Bringing the alpha down gives us just a to the log of x, where a is defined as e to the alpha. So you have some sort of composition going on here the same way. Now we can use the chain rule and our fact of using the similar derivatives. And if we go through and calculate what it ends up being, we do end up getting our alpha times x to the alpha minus 1. So this is the power rule for the general case. We needed a lot more machinery, including our inverse function and monotonic function machinery, in order to get to this point. But that'll do it for us today. We've talked about a little bit about the derivative, how it's defined, and how it can, some of the shortcut theorems, quote unquote, that we can use now that we've kind of derived some things with the derivative. What we haven't talked about, and what we'll discuss the rest of this week, are some of the applications that derivatives give us. We want to, of course, have all of these shortcuts so that we can make some of those proofs a lot nicer, a lot easier to kind of wade through. So we do a lot of this here without really any kind of application for it, so that in the future, we can talk about things like the mean value theorem, L'Hopital's rule, Taylor's theorem, and more. So we'll be doing that in the future discussions. But that'll do it for us today. Thank you so much. Have a wonderful day.